Okay, so today I'll be talking about the complexity of some set partitioning formulations for the capacitated vehicle routing problem with stochastic demands. This is joint work with my supervisor, Ricardo Fukasawa. So here's an overview of what I'll be looking at today. First, I'll be going over the definition of the deterministic vehicle routing problem and a vehicle routing problem with stochastic demands. I'll be talking about the set partitioning formulation we'll be looking at, the pricing problem for this formulation, and then what happens when we add in stochastic demands. And then finally, I'll be talking about the complexity of the pricing problem and two cases for demands specified as a set of finite scenarios and independent normal demands. So here's the vehicle routing problem. If you haven't seen it before, it's on a graph G with a set of customer nodes V plus and a depot 0, a set of edges that each have a length, and then we have M vehicles, each with capacity Q. So each customer has a demand DI, and we want to find a set of routes that satisfy all the customer demands and respect this capacity constraint, that the sum of demands on any route is less than or equal to the capacity of the vehicle. And then we just want to minimize the total distance traveled. So here's an example solution to this problem with 4 routes. So now, when we have stochastic demands, a few things change. So first, customer demands are now random variables, and their actual values will be realized after we plan the routes. We now have expected capacity constraints. So the sum of the expected demands on each route must be less than or equal to the capacity. And we can now have route failures if the demand on a route exceeds the capacity. So for example, I could be traveling along this red route here. Maybe I get unlucky, a few customers have higher demands than I expected, and I end up exceeding capacity at this vertex. What we'll do in this case is we'll do a recourse action and do a round trip to the depot and back, and then continue the route as planned. There are some other policies that people look at in the literature, but this one is simple computationally, so it's commonly used. And so now what we want to do is we want to minimize the total expected distance traveled, taking into consideration the costs that will occur from route failures. So this is the type of formulation we're going to be looking at. Set partitioning formulations like this are interesting to us because they're very effective for very similar problems like the deterministic problem and the vehicle routing problem with time windows. So we have the set R of all feasible routes. C sub R is the expected travel cost of route R, and this takes into consideration the expected failure cost as well. Alpha sub IR is the number of times vertex I appears on a route R, and then we have a variable for each possible route. So we just want to minimize the expected travel cost such that each vertex is visited at most once, well, exactly once by all the routes, and that we're using M routes. And so because we have exponentially many variables, we're going to solve this via a branch and price algorithm. So a big component will be pricing these routes to find what routes to add as we solve the problem. So the pricing problem is to find a feasible route of minimum reduced cost. In the deterministic case, solving the pricing problem for routes that do not contain cycles is strongly NP hard, so it's not really feasible to do this. The solution in this case is we relax the set of routes to be all capacity feasible Q routes, and these may contain cycles. So we just allow our routes to contain cycles. They still start into the depot and have to respect capacity, but they can have cycles now. And then if they're acyclic, then we denote them as an elementary Q route. So allowing Q routes allows us to do a pricing via dynamic programming instead. You kind of track the minimum route that reaches a vertex with a given demand and then apply dynamic programming over that. So this is then weakly NP hard with O n squared Q time complexity. Since we're usually not concerned with very large capacities, this is good for us. So now the question is, can we do this for the stochastic case as well? And the answer is we cannot exactly price two-stage cost for Q routes in the same way. So why is that? The main problem is if a customer appears twice in a Q route, that's equivalent to having 2 customers with perfectly correlated demand, even if all the demands are independent. And in essence, the problem this creates is we have to keep track of who we visited previously. So as an example, we consider these 2 routes R1 and R2 with all demands normally distributed with mean 1, variance 1. So you can see they look like they should be basically the same, right? They each visit 3 customers and then return to the depot. but in fact, they have different cumulative demands. R1 has a cumulative demand with mean 3 and variance 3, but R2 has mean 3 and variance 6, because when you revisit 1, the variance actually increases by more than just 1. So this is the main problem that having stochastic demands provides. So now I'm just going to quickly talk about some of our results. So for when demands are specified as a finite set of scenarios, we found that the pricing problem for finding the two-stage cost minimum Q root is strongly NP hard. So I'm just going to quickly give a proof sketch of this. It's a reduction from the Hamiltonian cycle problem on a graph G. So we're going to construct an instance of the pricing problem with these edge costs. So the main thing to note is edges that are instant to the depot have a very large cost, and all other edges have a negative cost. And then we set up demands like this. We have a scenario for every vertex. So we're going to have n scenarios in total. And each scenario has one vertex with demand n, and all other vertices have demand 1. And then we set the vehicle capacity to be 2n minus 1. So the way this is going to work is, because of the way the demands are set up, any elementary route that doesn't contain any cycles is going to have no second stage costs. Because of the demands, there will be no failures in any scenario. But if a route is non-elementary and contains a cycle, it'll visit one vertex twice and will have at least one failure. So that will create a large second stage cost due to these edges. Because of the way these edge costs are set up, once we leave the depot, we're also going to want to have a route as long as possible. So in essence, the route this is going to find is the longest elementary route. And then we can just check if that's a Hamiltonian cycle or not to determine whether the graph G contains a Hamiltonian cycle. So that's our result for demands with finite scenarios. Now I'm going to talk about our results for independent normal demands. So first I need to define this function, rfail. This just accounts the expected number of failures of a route with cumulative demand mu and sigma squared normal. So then we have this theorem. Suppose there exists a polynomial time algorithm for computing the minimum two-stage cost Q route for demands normally distributed and independent under the following assumptions. Mu I and sigma squared I are all polynomially bounded in n. All elementary operations on real numbers can be done in O1 time, and rfail can be computed in polynomial time in n for mu and sigma squared polynomially bounded by n. If all these hold, then there exists a polynomial time algorithm for the Hamiltonian cycle problem. Now note, this is not exactly a proof of strong NP hardness, because we have some of these extra assumptions we needed to use. And in addition, our edge costs and our construction are very large because they depend on this function, rfail. So we weren't able to get a proof of strong NP hardness, but it is a suggestion that this problem may be harder than we think. So the proof sketch is basically the same idea as the scenario case. We want to force the minimum cost route to be the longest elementary Q route. So we're going to construct an instance with all demands normally distributed with mean 1, variance 1, a capacity of n plus 0.5. And then we're going to define these two constants that will be very large. They're going to be at least exponential in n. And then we define these edge weights. So again, we have edges incident to the depot are very large, and edges not incident are negative. So the general idea is the large constants for depot edges are going to cause a very large second stage cost. And we want to exploit the slightly higher probability of route failure due to a higher variance in non-elementary Q routes to force the minimum cost Q route to be elementary. Unfortunately, because they're all independent demands, we can't do the same thing where an elementary route has no second stage cost. We just have to make it slightly worse for non-elementary routes. And then we can compute that there is a threshold value gamma such that the minimum two-stage cost being less than or equal to gamma implies the solution is going to be a Hamiltonian cycle. So those are our results. I'll just talk briefly about what this implies about the problem. So in general, we show that solving the two-stage cost pricing problem is hard. It's strongly NP hard, and it may even be hard for independent normal demands. So for future work, first we want to settle the question of whether the two-stage cost pricing problem can be solved in polytime for independent normal demands. And secondly, try and develop a branch and price algorithm that can also account for scenario demands. So there was a similar problem with the CC or chance constrained vehicle routing problem where pricing was strongly NP hard, but that was overcome by combining two formulations. So we're hoping a similar approach may work here. Thank you. Any questions?